Hey guys, so this lesson is a reinforcement of Objective 2, and Objective 2 is to be able to identify the domain and range of a function. The words that we're going to deal with right now are domain and range. So the domain is the set of all x values, and the range is the set of all y values. We even went on to elaborate a little bit more on domain and range in the first video, so if it's something you might need to reinforce, definitely go back and watch it again. In class, we did an example to identify the domain and range. And every time for right now, I'm writing in order from least to greatest. They're not going to always tell you to put things in order from least to greatest. It's sort of up to you to know and understand that that's really how we should go about doing things. I'm going to put a little star right here, and I'm going to add a set of, and I like the language of using a set of. Set is actually a very important word in math, so we need to get used to set builder notation, which we spoke about as well. So right here, this is the relation, or in this case, actually the function that we were given. The ordered pairs are 1, 1, 2, 4, 3, 9, 4, 16, and 5, 25. Domain is all of the x values, which are 1, 2, 3, 4, and 5. And our range is all of the y values, 1, 4, 9, 16, and 25. This is what we call a finite list. You can count the items here. By listing it this way, we are not including the numbers in between. Oh, well, can't we just say that y is equal to x squared? And while that does seem pretty great, right? You plug in 1, you get 1. You plug in 2, you get 4. 3 gives you 9. 4 gives you 16. 5 gives you 25. This equation has a different domain and a different range than this set of ordered pairs. This set of ordered pairs has only 5 numbers in its domain. This domain is all real numbers. An equation or a graph can look very different than similar ordered pairs from a set of ordered pairs, from a table of values, or a mapping diagram. All right, so I have an example 1b for us to do. Look at all your x values. And if you said you should start with -5, you were correct. So -5, -4, -3, -2, and -1. Oops, almost. Just because -5 is here doesn't mean -125 has to go there. It just happens to be the smallest y value. All right, here's -64, -27, -8, and -1, and then we close out our bracket. Here's the next example. We had a mapping diagram instead, and mapping diagram looks something like this. For our domain, again, you just go right to the input, which is your list of x values, and you list them all from least to greatest. And the range, you go to the output, which is your y values, and we listed those from least to greatest. Now, here's a bonus example. Here's example 2. B, in the independent box, I have -7, -1, 2, 5 halves, and 3. And in the dependent box, I have 0 and 100. So my domain from least to greatest, and if you make your mapping diagram nicely, it should already be in order for you. So -7, -1, 2, 5 halves is next. Make sure you know that your which fractions are which size, and 3. And then for my range, I just have 0 and 100. Third, we had to identify the domain and range from a table of values. Our domain and range were easy peasy from there. So threw in an extra example to help us extend on that. So example 3b, domain, not so bad, 0, 1, 4, 9, 16, and 25. And I'm going to fill in the range, and it works the same way. 0, 1, 2, 3, 4, and 5. 3c. 3c is a little bit more interesting here. I have 128, 16, 105, 16, 186, 16, 114, 16, 224, 16. Now, from least to greatest, we will be looking at 105, 114, 128, 186, and 224. Sorry, I'm squeezing it over here. And my range, I have 16. That's it. So whenever your domain or range only has one value in it, or you have a few random values, you really want to use set builder notation. Here in example 4, we were dealing with finding domain and range from a graph. So in class, we had an example that looked quite different than things you've graphed in Algebra 1, and it looked something like this. The numbers might have been slightly different, but this is actually called a rational function, and we will become more familiar with them later in this school year, all right? This is a rational function. Now the actual graph, I want to point out, the part that's really the graph is here in pink. So I'm going to circle the word graph in pink here. The purple, you mentioned the word for the purple. The purple part over here, these are called asymptotes. right? Make sure we pronounce it correctly, spell it correctly. So we have a vertical asymptote right there, and we have a horizontal asymptote right there. Your vertical asymptote really has a lot to do with restrictions on your domain. The domain and the vertical asymptote are very, very related. The horizontal asymptote is not as closely related to the range, however. The horizontal asymptote is actually more connected to a concept from calculus, limits at infinity and negative infinity. And we'll talk about that in the future. So they both turn out to be these dotted lines that we add to our graph to help us guide our drawing, but they're both coming from entirely different places, all right? They're not for the same reasons. Now, my domain, because I'm dealing with the graph here, and this is not discrete, it's continuous. Because I have a continuous equation here, and the graph goes on and on and on forever, okay? The arrow means it continues, and it follows the same behavior. The asymptote is, we're going to get much closer to it. We're going to get very close to it, but we will never touch an asymptote. A vertical asymptote you'll definitely never touch. Horizontal, again, however, you may cross horizontal asymptotes. It is allowed. So if I'm not showing it cross anywhere here, it's pretty fair to assume that it will not cross. Because of the way the drawing is, you're allowed to make certain assumptions right now. So for the domain, you have to remember your negative infinity should always be in a left position in this interval notation. And if you ever use a negative infinity and it winds up over here on a right side, whether this spot or even this spot, you have to go back and make corrections because you messed up. It's a very common mistake, okay? Negative infinities are always in the left. It kind of looks like an ordered pair, right? The first one will never be negative. The second one will always be positive. Got it? Positive infinities whenever you're using them, okay? So we will reiterate that in class again. But now we start all the way down on the left, okay? You pretend that this was somewhere where you can be standing right over here and you look up. Will you see graph? Yes, you will. There is graph in this entire x domain. So the x-axis, we're showing the domain. There's graph out there at negative infinity, going along, going along, going along. There's still x values. It doesn't mean that there's still graph continuously attached here. For each x value, there exists graph, okay? Here at 4, though, the asymptote, we're not touching it. That's why we excluded 4 from the domain. The parenthesis means it's not included. The U is the union symbol, and it unites the two intervals of the interval notation. We continue from left to right. Again, domain goes from left to right. So if you have to make some note of that, left to right, maybe actually spell out the full words. Sorry, I'm just shorthanding it. You would keep going until infinity. Range, now we have to go from the bottom up to the top because you always start at the lowest y values and work your way to the biggest. So this one we're going from the bottom to the top, all right? Down here, if you're all the way down here at the bottom of the y-axis and you look left or right, do you see any graph? Does this y value of negative infinity include graph? Yes, it does. It goes down forever. So you're climbing up the y-axis. You have graph, you have graph, you have graph. It's accounted for. Where do you not have graph? At 2. So here at 2, no graph. And we pick up right after 2, and we continue up with graph upward until infinity. This is going to take a while to sink in for a lot of you, okay? It gets better when you have equations to support the pictures, the graphs, and vice versa. And it will come with time. So here's a couple more examples to just get us a little bit more comfortable. Here's another graph. The red is the graph, and that's all there is to it, okay? There's not this part right here. Sorry, the drawing's not great. This is a closed circle. This, on the other end, is an arrow. So this closed circle, there is no more graph anywhere this direction, and this arrow means it's following in this kind of shape going that way, okay? Now, domain and range. My domain is going to go from left to right. If I'm all the way down at negative infinity, all right, if I continued my axis at down at negative infinity, do I see any red graph down here? No way, Jose. Keep going, keep going, keep going. I get over here at the origin. This is where I first see graph, and it is included. So my domain is going to start at 0, and I'm going to go until infinity because it never stops. It's continuous from there on out, and the arrow tells me my x values go down forever and ever and ever, okay? And then I use a parenthesis. Bracket again means that you can achieve that value, you will get there, and a parenthesis means you will not ever get to that number, and infinity is more of a concept than a number, so you can't get there. And strangely enough, the range. The range from the bottom, and we're working our way up. Down here, is there anything? No, 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 no. Boom, right here, we hit it. So my range starts at 0, okay? My range starts at 0, and now my range is going up in y values. While this is going out, it's also going up. It moves to the right faster than it moves up, but it is moving up nonetheless, all right? If your bank account is getting bigger and you're getting more and more money, slow and steady, better than nothing, so there it is. So it's going to go up to infinity. Now, while the domain and range are both the same thing, the graph does have its own interesting shape, okay? Its own relationship with x and relationship with y, and the behavior isn't a steady line or anything like that, okay? It does have a bit of a curve to it. We call this type of a curve concave down, okay? Concave down looks like a frown. Concave up looks like a cup. Concave down looks like a frown. Also, some other phrases to keep in mind for this year, we would say that this function, because it is a function, is decreasing on its entire domain. I know right here there's this like magical jump from here to there, but this is not in its domain. So from left to right, we always read from left to right. It's not going up ever, okay? It's always getting lower, and then even here it's always getting lower. This we say is always increasing on its domain. Next example we have looks like this, and we should be slightly familiar with something like this from Algebra 1. This right here is what we call a quadratic equation, or this picture, this graph is what we call a parabola, parabolic curve. So my domain, if I go all the way out to negative infinity, is there going to be graph to account for out there? Yes. This parabola is going to get wider forever and ever and ever. So any x value will be accounted for in this situation. Now I keep going. Once I get it here, you could see it, of course, a little bit better. Here it is. My x value keeps going, keeps going. Looks like I hit a maximum. Okay, we call this a maximum point. This maximum value, the value is 4. The maximum point is 5, 4. Okay, again, the word point in math means ordered pair. So a maximum point of 5, 4. However, a maximum value of 4. Parabolas that open down, concave down, looks like a frown, have a maximum value. Then we keep going, and we're getting smaller, and it goes down forever. But keep in mind, it is also getting wide forever. That means every x value is accounted for. So what does that say about our domain? We can either write negative infinity until infinity, or we can write something like this symbol, which means all real numbers. Okay? So that means all real numbers. We have to specify real because there are numbers called imaginary numbers. Sometimes you'll have to specify when you say no real solution, because sometimes you have imaginary solutions. All right, now the range. Again, we're at the bottom of the y-axis, and we're looking from left to right. Do we see graph? Yes, it goes down forever. We actually see graph twice, but you're allowed to have something fail, say the horizontal line test. It just can't fail the vertical line test. Now, I see graph starting at negative infinity, working my way up. Again, if you do an example like this, I often see people say 4 to negative infinity, because you guys want to go from the top to the bottom. No, cannot do that. Working our way up, okay? Working your way up, and then we get to 4, and there is still graph accounted for at 4, so that's part of our domain. I'm so sorry, that's not domain. Part of our range, and it is included, so we're going to use a bracket. Now, interval notation is definitely the best way, in my opinion, and I'm sure in many other math people opinions, to write domain and range. However, you may occasionally see something like this. Y is less than or equal to 4. This really is the same thing. We've been practicing interval notation and inequality notation as well as number lines. So all good in the neighborhood. Really, if you see this in a book or on a website somewhere, it is the same thing, but I prefer that we practice writing this way to help prepare you for bigger things in the future. Here we have our last example, and probably one of the more important types of examples, and also one of the more challenging types of examples. When we are at a point that, like we are right now, where you maybe aren't that experienced with graphing every type of equation, it is a bit of a struggle for some people to really comprehend domain and range. They really go hand in hand, equations and pictures, to really put it all together. So we use this example today in class. This example of y equals x squared is something that we should be mildly familiar with, all right? In Algebra 1, you graphed the parabola, y equals x squared. So if you wanted to kind of pull this from your mind, your domain and range from a picture in your mind, it wouldn't be a terrible thing, but you really need to understand how the equation works. But from an equation, when you're doing your domain, you really need to identify, is there an x value that would cause me any sort of mathematical discomfort when I try to evaluate the equation at a certain x value? Is there an x value we cannot square? We could square negatives. Negative 1 squared is 1. Negative 100 squared. We could do that, right? So we get 10,000. Plug in, 15, positive 15. 15 squared, 225. So really, you could square negatives, positives, 0. We could square fractions. 2 over 3 is 4 over 9. We don't have any issues. That is why your domain is negative infinity to infinity, or the real numbers, the set of all real numbers, this R with an extra line in it. Okay, now the range. Range, I'm not always going to ask you to do the range right now, because certain equations Doing the range is a bit of a stretch. I will show you a few tricks in the 5A, 5B, C, and D, but some of them you're going to sort of memorize or learn tricks for now, and then we'll piece it together throughout the school year. What is the smallest thing we can get for our Y value, which is dependent upon my X value, based on what I plugged in for X? Now, I'm allowed to plug in anything for X. If I plug in -5, I get 25. -4, I get 16. -3, I get 9. I'm getting smaller, right? -2, I get 4. I plug in -1, I get 1. I plug in 0, I get 0. Well, what do I have to plug in to get a negative? Will I get a negative? We said no. We talked about this, okay? Give it some thought if it doesn't click yet, but you'll never get a negative. The smallest thing you'll ever get when you square something is 0. From there, it can grow indefinitely, because if you square infinity, guess what you get? Infinity, okay? So from an equation, it's going to be a little harder for some of us, but we'll get there. Slow and steady wins the race. So here is our next example. Sorry, it's a little blurry there. Okay, 5B is our next example. Y equals 2x plus 7. Again, this should be another example that is really familiar to you guys. We've graphed this type of equation for many years. This is a linear equation, okay? The slope is 2. The y-intercept 7. You should be comfortable with this. Now, is there an x value that you can't double? Can you double a negative number? Can you double 0? Can you double a positive number? I can't think of a number I can't do that to, so sounds pretty good so far. And is there a number you can't just add 7 to? I can't think of anything either. So what does that say about our domain and range? Well, our domain, that means, is -infinity until infinity, or again, all real numbers. I will probably write it like this most of the time. I'm giving you the option right now, though. If directions ask for interval notation, I would definitely do that. This is actually the set of all real numbers, so if you were doing set builder notation, like we did earlier, that kind of fits into that family, all right? It's the same type of notation. It's just special to cover every real number: decimals, fractions, positives, negatives, repeating decimals, non-repeating decimals, terminating, non-terminating, combination of repeating, or what is it? Non-repeating, non-terminating, irrational numbers. They are real. Now the range, same idea, with a linear equation that looks something like this, okay? It's increasing, slope of 2, y-intercept of 7. It goes up and down forever, so my range is the same. It's -infinity until infinity. I'm telling you, the more we do, the better you're going to get at these. Here, square root of x, and then square root of x minus 2. Is there an x value that we are not able to take the square root of? Now, if you have to pause and think about it before I tell you, then you can pause and think about it. But the type of number we cannot take the square root of would be a negative number. You can definitely do the square root of 0. That's 0. We can do the square root of 1. That's 1, right? Square root of a decimal, sure. Would you maybe need your calculator, some of you? Yeah. Okay, so square root of a positive number, that's fine. Okay, my little happy face right there. However, if I try to take the square root of a negative number, okay, when you do that in your calculator, it says domain error. That means then my domain, my options for x, my domain, are from 0 until infinity. My range, when you take the square root of something, will you get, there's nothing out front here that indicates otherwise. Will you get a negative answer? No way. You're going to get positives or you're going to get 0. So we don't say you get positive answers, we say non-negative, which includes 0. Now, this one we could think of and conceptualize. This one, it's going to be a little bit more to it because it's going to tie in some more algebra steps. So what should we do to ensure we always get these right? This thing underneath the radical is what we call a radicand, all right? Radicand, like this. The radicand under the radical, I'll color this over with yellow in a second. The radicand has a special rule. Let's even move this out of the way a bit. Okay, we just said you cannot take the square root, of negative numbers. So that means the radicand, whatever the radicand is, must be greater than or equal to 0. It's easier to say what it can be than to say what it cannot be, because how do you say like cannot be less than 0? Then you're crossing on a less than sign, things are going to get messy. So squeezing over here, my radicand has to be greater than or equal to 0. From there, we're going to use algebra and we're going to solve for x, and that's going to get us what we need regarding the domain. The range, you might still have to reason out a bit, so let's look at this next one. I'm going to do this algebraically. The radicand is x minus 2. It's in a radical, it's in a square root. Now also, keep in mind, there's an invisible 2 in this little hook right here, okay? This is called the index. It's an even number. 2 is even, because when you take a square root, you're looking for something times itself an even number of times, twice, that equals that number. Whenever you multiply something by itself an even number of times, you should get a positive answer. So this rule only applies to radicals with an even index, so square root, fourth root, sixth root, etc. So x minus 2 has to be greater than or equal to 0. Add the 2. Do not just sit there and think like you have to guess and check your life away. That means x is greater than or equal to 2. If you need to picture it on a number line before you do your domain, then go ahead, draw it. Don't try to be a hero and do it in your head, because then you'll get it wrong and be sad. So my domain is from 2 until infinity. My range, however, is not 2 until infinity. Whatever I take the square root of, the smallest it can be is 0. Usually if you play around with this number, it kind of tells you a bit. 2 minus 2 is 0. Square root of 0 is 0. So help this out with that. If there were a negative out front, it might create it to go upside down, okay? So it's going to be from negative infinity till 0, but these are all things we're going to learn later, so don't stress about that right now. Now, before I move on to the other two, this one right here, see the domain and range? This is actually the equation that corresponds to this graph. See? Picture-wise, this is what it looks like. If I plug in 1, I get 1. Well, that's because the square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. The square root of 0 is 0, and so on. Okay? Back over here for the next two examples. So we have, these are the special types you'll see. Radicals, square roots, even roots, and rationals. This right here, these are a bit more like the one we had with the asymptotes, okay? Now, our domain. Which x value is sort of like toxic for this type of equation? What x value, what number plugging in for x will you run into trouble? And that number in this case is 0, because you're not allowed to divide by 0. So this piece that we're focusing on is not a radicand this time, but our denominator. Same over here, we're going to focus on the denominator. Now in this case, instead of saying what we can equal, we're going to talk about what we can't equal. So denominator, so writing notes down, denominator cannot equal 0, and then again, you're going to solve for x, okay? What's my denominator? X can't equal 0. Well, really solve for not x, sort of. So x can't equal 0. What does that say about your domain? It's everything else. Everything else, negative infinity until 0, union 0 until infinity. Sorry, it's a little squeezed. Now my range, okay, I'm not going to expect you to do the range for something like this unless I gave a picture, but if you wanted to remember, if they're both x to the first power, little trick, and you'll understand it in the future, if they're both x to the first power, the biggest power on top and bottom of something like this, your range will probably exclude whatever number you can create by this coefficient and this coefficient, so 1 over 1. So really my range, I'm just going to write it a little shorthand right now, is y cannot equal 1. So that tells me to write negative infinity until 1, union 1 until infinity. Again, don't worry about this too much, but if you kind of keep it in the back of your brain, it'll come up another time. Domain, denominator, cannot equal 0. Bring over the 8. X cannot equal negative 8. So what can it equal? Everything else. Negative infinity until negative 8. Union, negative 8 until infinity. Sorry, again, it's very squeezed. My range. Now the new rule. These both have x to the first power. If the bottom x has a bigger power than the top x, well, on top, that's really next to the 0, because anything to the 0 is 1. So this is a 0 and this is a 1. If the bottom's bigger, well, y cannot equal 0. Even if you thought of it, actually, you know how you don't have an x up here? Let's look at it this way instead. Better way to think of it. That means that you have really a 0 x to the first plus 1, right? And what's 0 over 1 equal? 0. So that's what y can't equal. How about that? So my range in interval notation, negative infinity to 0, union 0 until infinity. So we have some notes thrown in here. When you have this denominator situation, denominator cannot equal 0, and you solve for x. Well, solve for not x. Solve for what x can't be, and then say the domain is everything else. If you have radicals, square root, 4 through even roots, we take the radicand, the thing under the radical, and we say it must be greater than or equal to 0, and again, you solve for what x can be. So hopefully this helps clear up any concerns. Sorry, it was a little longer than I hoped for.